Hello, friends, and welcome again to our sixth lesson in the Lean Six Sigma. And in the last lesson, we discussed the linear and the non-linear regression equation with the calculation of the coefficient of the determination, in where we explained that the coefficient of the determination is mainly used to measure the accuracy percentage of the prediction equation. But a question is, what about if we have more than one independent variable x? In the last lesson, we discussed the both example for the linear and the non-linear regression with one independent variable x only. But what about if I have two or three independent variables that will impact on the output, the y? So today we will discuss the multiple regression, and we will understand how we can conclude a regression equation with more than one independent variable x. Today we shall take a good working example for those gentlemen who are mainly working with the production, in where we will conclude a regression equation, a multiple regression equation, used mainly to predict the time of the production. Don't go away.
So the multiple regression is a statistical method to create a prediction equation for a dependent variable y and multiple independent variables x's. Please make sure that you've watched the last lesson where we explained the linear and the non-linear regression equation, as it will help you to understand better the lesson of today. Okay, so let's take our example now to understand better the multiple regression. Adam is a production engineer who's working in a factory specialized in building different types of electrical panels. He's been requested by the factory management departments to provide a production time study to be used as a reference for the time and cost planning. The major problem that Adam is facing is the high variation in the technical specification from product to other, which will make it difficult to have a clear time estimation for the production activities. So for those engineers who are working in the field of the production of control panels, they know very well how far is the variation in the technical specifications and the design requirements for the control panels, which lead to have a high range of time consumed in the production, which is in fact a little bit problem to have a time study estimation for those kind of products. So let's see how the multiple regression can help to solve this problem. Adam invited his team for a brainstorming workshop, and they all agreed that there are two major factors which have a strong impact on the production lead time: the number of the wires, which can be found in the schematic diagram in the tables of the wiring termination, and the number of the electrical components. So one of the team came up with an idea to apply a multiple regression equation in where the dependent variable y is the production lead time, and the first independent variable x1 is the number of the wires, and the second independent variable x2 is the number of the electrical components. Now, if we refer to the multiple regression equation, the y is the predicted value, the b naught is the interception, the B1 is the coefficient of the first independent variable, and the beta 2 is the second coefficient for the second independent variable, which is the number of the electrical components. So our equation should be like that. The production lead time equal the intercept plus beta 1 multiplied with the number of wires plus beta 2 multiplied with the number of electrical components. So as we can see, all what we have to do is to estimate three variables: the intercepts, the beta 1, and the beta 2. How can we apply the multiple regression in that example? And that was the question of the production supervisor. So Adam replied that he would prepare a production form in where they will select randomly 25 panels with different technical specification within 7 days. So we are speaking here about a data collection plan. So let's see how it will look like. So this is the production form which Adam designed, and we can see that they collected 25 panels. Each panel contains different number of wires and different number of electrical components. There's the cycle time in hours. So each panel has the number of wires, the number of electrical components, versus the cycle time hours. Now, I would prefer that we go to the Excel sheet so we can understand how we can extract the multiple regression equation. So let's go. Okay, so here we have the production form where we have all the data that we need. Now I will show you two ways to extract the multiple regression equation. The first one is the manual way, the old days, and the second one is the Microsoft Excel. The reason behind that I show you the manual way is to understand how the results were extracted. So as you can see, this is the formal equation for the multiple regression, and all what we have to do is to find the beta naught, the beta 1, and the beta 2. So here is my table where the first column is my dependent variable, the y, and the second and the third column are my independent variables, the x1 and the x2. So to calculate the intercept, I have an equation where beta naught is equal to y bar minus beta 1 x1 bar minus beta 2 x2 bar. To calculate the beta 1, though this is the formula is sigma, or the sum of x2 squared multiplied with the sum of x1y minus the sum of x1 multiplied with x2 multiplied with the sum of x2y divided by the sum of x1 squared multiplied with sum of x2 squared minus the sum of x1 x2 squared. And the beta 2 is the sum of x1 squared multiplied with the sum of x2y minus the sum of x1 multiplied with x2 multiplied with the sum of x1 multiplied with y divided by the sum of x1 squared multiplied with the sum of x2 squared minus the sum of x1 multiplied with x2 squared. And here you can see each parameter has its own equation. So if I want to calculate the sigma x1, the sum x1 squared is equal to the sum of capital X1 square. So the sum of the x1 square should be that column. here. So that will be the number of 186. Let me highlight it. This should be my sum of x1 square. So as you can see, there is a difference between the small and the capital letter. So to find the sum of x1 square, that will be the sum of the column of x1 square, which is 186,552,200 minus again the sum of x1 squared, the same, divided by n, where n is the sample size. So the sample size is the number of the data, which is the 25. So you can see here the count is 25. And the sum of x2 squared will be this column as I highlight. So the sum of x2 squared, the capital X2 square, will be this one as per the highlighted. And the n, where n is the sample size, 25. And the sum of the x1 multiplied with the 1 will be the sum of x1 capital multiplied with the y. So here I calculated the x1. So the x1, the number of y is 300 multiplied with the 3.8. That will be 1,140. And I repeat that equation till the end. So this one will be the sum of the x1 capital multiplied with the y as per the highlighted. Then the sum of x2y, that will be the x2, which is the number of electrical components here, 6 multiplied with 3.80, that will be equal to 22.8. And I repeat in the same column, and that is the sum of x2 multiplied with y. I have the last one, which is the sum of the x1 multiplied with x2, which is the sum x1 capital X2. And that's the result of multiplying the two independent variables together. Then I take the sum of all those multiplication, and here I have it. Okay, so it's a matter that I calculate all those parameters. So at the time that I find all those parameters, I just follow the equation till that I can find the beta 1, which is the coefficient of x1, and I calculate the beta 2, which is the coefficient of the second independent variable, and the beta naught, which is the intercept. So based on that, I can rewrite my regression equation, that the cycle time in hours, which is my dependent variable, will be equal to 0.531, which is the intercept, the 0.531, plus the first coefficient, which is the beta 1, plus 0.00539, which is the beta 1 here, multiplied with the numbers of wires, plus 0.2156, which is the beta 2, the second coefficient for the x2, which is the number of electrical components. Now, I passed very quickly in that example just to show you the equations of the calculation for the three estimations: the beta naught, the intercept point, the beta 1, the coefficient of x1, and the beta 2, the coefficient of the second independent variable. But indeed, it's much easier and much faster to calculate the multiple regression equation through the Microsoft Excel, as you will be able to find the answer in few seconds. So let's repeat that exercise in a new sheet so we can see how we can extract the multiple regression equation in the Microsoft Excel. So if I look to that table, here I have my dependent variable y. I will highlight it in yellow. And the number of wires, I will say it's x1, my first dependent variable. And the number of the electrical components will be my second independent variable. And I highlighted in yellow so we can all see it very clear. Now, the first step to find the multiple regression equation, if I go to data, I go to data analysis, and then in the data analysis, I will go and see the regression. So let's see where is the regression. Here I have my regression, and I will just highlight my y dependent variable, which is the cycle time. I will select it. I click enter. And then I go to the input X. I have two independent variable. So I will select the both columns. And I click enter. I will click on the labels because I selected the titles of the columns. I can choose the confidence level for the 95%. The output range, I will select the location, the cell location of the results. I can put it here. I click enter and I click OK. So let's see what Excel gave it to me. Now, first data is the correlation. So let me highlight it. This is the correlation factor. And this is showing that as I have a very strong positive correlation, as it is 0.98. The R square is the coefficient of determination. And here it's showing that the accuracy of my prediction is almost 96%, which is considered a very strong value. Now, it's very important also to look to that data, the F statistics and the significance F. This is an indication if I have a strong prediction that since that the significant F is less than 0.05, that means that's a strong regression. The entire regression is considered to be strong. So let me highlight it in yellow. So that's another good indication. Now, there is the intercept, the number of the wires, and there is the number of electrical components. So that is my beta naught, and the second one is the beta 1, and the third one is the beta 2. Now, also look to the p-value. The p-value here, if you see that the p-value for the number of wires and the number of electrical components which is less than 0.05, that's an indication that each of those parameters has a strong impact in the regression equation. In case that you see any number here or here is higher than 0.05, then you have to know that this parameter has no impact on the regression equation. Okay, so as per the results that we have here, we can extract directly my prediction equation. The prediction equation here will be that the cycle time in hours, so let me write it for you, cycle time in hours equal my intercept is 0.53142 plus my beta 1, which is the coefficient of the first independent variable, the numbers of the wires, will be 0.00539 multiply with numbers of wires, okay, plus the beta 2, the second coefficient, which is 0.2156 multiply with the number of electrical components. Okay, so as an example, if I want to estimate the time of the production for a new product, the number of wires is, let's say 760, and the number of electrical components will be 6. We want to estimate now the cycle time in hour. So the cycle time in hours will be, I have my intercept point 0.5314 plus my first coefficient for the number of wires is 0.0053916 multiply with the 760 plus the second coefficient is 0.2156644 multiply with 6. Let's see. It will give me around the 5.92 hours, almost 6 hours, we can say. So that will be the estimated time for a product which has a number of wires, 760 wires, and number of electrical components is 6. So let's compare now this result with the actual value that we reported before, okay, to see how far is the error percentage. Okay, so we mentioned 760 wires and 6 electrical components. So let's see if we have any numbers of wires. 760. Yeah, here we have it, 760. So you can see here in the actual value, it was almost 6.4 hours. So if I just make a small efficiency calculation, I have here 92.5% is the accuracy of my prediction. So from that example, I hope that I could explain for you how can we extract the multiple regression equation and how to verify the accuracy of the prediction equation through the correlation factor, the coefficient determination, the F statistics, and the significance F, the p-value for the independent variable is less than 0.05. This is a good indication that independent variable has a strong impact on the regression equation. If it's is higher than 0.05, then it can be ignored as it doesn't have any impact on the multiple regression equation. So let's go back now to the PowerPoint presentation. Okay, my friends, so here is my table, and this is the multiple regression equation. And as we summarized that in the multiple regression equation, there are mainly three parameters that you are estimating it. The beta naught, which is the intercept, the beta 1, which is the coefficient of the first independent variable x1, and the beta 2, which is the second coefficient for the second independent variable x2. And in that example, we mentioned that the dependent variable is the y, the production lead time, and the coefficient of x1 is the number of the wires, and x2 is the number of the electrical components. In where at the end we concluded the regression equation by looking to the intercept in the last table. The intercept value, the number of wires, this is the coefficient for the number of the wires and the coefficient of the number of the electrical components. And we give an example, a calculation example to predict the the production lead time by inserting the number of wires for the 760 wires and the number of electrical components 6, and we compared our predicted value with the actual value, and we found that we have an accuracy percentage of 92.5%. I thank you for your good watching and listening. For the next time, thank you.